My meeting has started, Julia, okay? Uh, Hello.
Oh,
Oh, hold on. My speaker is off. Can you hear me okay?
I can hear you.
Great. I can hear you. We can get started if you want. Maybe we'll wait 1 minute and then we'll get started. Okay, Donovan, do you have any questions in particular?
Um, Not really. I haven't started on the practice exam yet because I wanted to go through all of the key highlight notes first and like do practice problems on those before I started the
Yeah.
exam. And from what I've done on that, it all makes sense because I started studying today, so
Uh-huh.
I don't have like I just was like a general like review of what you think would be on it is or like just a general view of the material would be nice, is what I'm looking for.
Okay. Let me see. There's a couple of other people that are just joining now. Um, we can go through um, questions as we. Let me also pull up. Um, So just in terms of what is in this exam, we have learned about systems of linear equations, and we have transformed those into matrix equations, something like AX equals B. And we've learned how to solve those using the augmented matrix. So something like this augmented with the column B over here, where this is the matrix A. And we have learned to row reduce. And as I said, maybe in some of the first days of class, the key of the entire course is row reduction, because everything ends up being everything so far boils down to row reducing a matrix. So learning how to row reduce correctly and to double check that your work is correct is really important. We have talked about once we have systems of equations or matrix equations, we have talked about the solution sets. And we've talked about how these can be, well, they can be empty, no solutions. There can be one solution, and there can be infinitely many solutions. And we know how to tell those apart from the row reduction. So we can do examples about that. But the row reduction, once we know in terms of the pivots, we know how to tell these apart. For example, we know there is no solutions. When there is a pivot in the augmented column, there is one solution. If there's a pivot in every row, there is infinitely many solutions. If there is no pivot in some columns, because then that will correspond to free variables, right? Then what else have we seen? Once we've moved on to writing matrices. So if I had a system, what we interpret this is as a linear combination of the columns of A is equal to B. That's what this is asking, is there a linear combination of those columns that give you B? And then we talked about the concept of linear independence. So when are there vectors? If you have some vectors v1, v2, up to vn, we say they're linearly independent if and only if the only combination of those that give me the zero vector, so these are linearly independent, if and only if all the lambdas have to be zero for that to happen. Okay, so that's an important concept. And then we reinterpreted these systems in a new way as linear transformations. So now we're talking about linear transformations from Rn to Rm, and they are given by some x is going to a times x. And then we have properties of these linear transformations. First of all, what it means to be linear. We need to know what that means, which is two different things. We have the t of a sum is the sum of the t's, and that t of a scalar is the scalar of the t. And then we've also looked into properties that you need to know how to determine if a map is 1 to 1, if a map is onto. And then we moved on to matrices. So with matrices, we know how to add matrices. We know how to scale let me scale first matrices. Matrices, and then we can multiply matrices if the dimensions match. Then you should know how to multiply two matrices. We also learn how to find inverses of matrices. So how to determine are they invertible first of all? And if so, what is the inverse? So there's a method that what we did is that to do this in this part of the test, what we do is we set the matrix A that we want to invert. We put the identity matrix over here, and then row reduce to see what we get. And if we are able to row reduce this side, the left-hand side, all the way to the identity, then actually what is on the other side is the inverse matrix. So that method allows you to see both if they are invertible and how to find the inverse by row reduction. But we have a big theorem that is the invertible matrix theorem that gives you all sorts of conditions for a matrix to be invertible. So if A is n by n, then we have a bunch of conditions that tell me when it is invertible. First of all, the definition is that there is some B that I can multiply it by on the right or the left and get the identity matrix. It has to have n pivots in echelon form, and etc. Conditions that are equivalent in this case to having an inverse matrix. So what I would like to do is just try to go through problems just to go over all these concepts. So if I can have anyone suggest a problem, then we can just illustrate all these concepts with examples from for example, I can do any example you want, but I think there's a lot of different problems in the practice questions that would be ideal to go through. Um, I'm I'm not looking at the chat. Yeah, if there were people in the chat, I haven't looked at the chat. Nobody in the chat. So do you have any questions in particular, any problems you want me to go through?
I think any of the problems related to spans would be nice to review.
Span. Number 4 or 5 in the practice test and span. Yes, I'm getting a phone call. Let me, 1 second, please. Okay, sorry about that. Let me get back to this. Where were we? So I'm going to look at problems 4 and 5. Those are about the span, so perfect. So let's see. Problem 4. Let me actually do this. Let me see if I can just copy and paste the image so we can all look at it. Um, Perfect. All right. So here they're asking me if this vector is in the span of these three vectors. So what they're asking me is, let's write those three vectors as like columns of a matrix. So this is 1, 2, 0, 3, 4, 3, 0, 2, 3. And or before I even do that, just what does it mean to be in the span? If this is V1, V2, and V3, and this is B, they're asking me if there are lambdas 1, 2, and 3, such that lambda 1 V1 plus lambda 2 V2 plus lambda 3 V3 is equal to B. Okay, so if I put that as a matrix equation, this is telling me A times lambda 1, lambda 2, lambda 3, is that possible? That is minus 1, 2, 0. So those are my three unknowns. So what I'm trying to do is solve the system of equations. So I'm trying to solve 1, 3, 0, 2, 4, 2, 0, 3, 3, and augment it to minus 1, 2, 0. Right? Right? Okay, so now I can row reduce this matrix and see what happens. So if I row reduce this matrix, I get 1, 3, 0, minus 1. Eliminate these 2 over here, and I get, so the second row minus the first row, minus twice the first row is going to be 0. 4 minus 6 is going to be minus 2. 2 minus 0 is going to be 2. 2 minus 2 is 4. And the third row is 0, 3, 3, 0 for now. I can row reduce this farther. This is 1, 3, 0, minus 1, 0, 1, minus 1, and I'm dividing by minus 2. So I'm going to get a minus 2 here, 0, 3, 3, 0. Okay. Let me know if you notice any mistakes, but I think this is okay so far. 1, 3, 0, minus 1, 0, 1, minus 1, minus 2. Eliminate the third row. I get, subtract 3 times the second row, and I get a 0. 3 minus minus 3 is 6, and 0 minus minus 6 is another 6, like that. And this is going to be 1, 3, 0, minus 1, 0, 1, minus 1, minus 2, 0, 0, 1, 1. Okay. Good so far? And now I'm going to notice, by the way, that the question is this in the span? Which means I don't even have to find the linear combination. I just have to answer if it is or it isn't. And now that I see that there is 1, 2, 3 pivots and no pivot in the augmented column, the answer is yes. And I can keep going and find the actual linear combination by solving this system, but I don't have to do any more because, well, I see that I do have a pivot in every column here, in every row, in fact, and therefore there is a solution. There is a unique solution. Okay, in this case, because also there is a solution because there is a pivot in every row and not in the augmented column, and there is one solution because there is a pivot in every column. So I have a unique solution. So this is way too thick. Let me scale this to unique solution. Okay. And that tells me that yes, for this one, the first answer is yes for this part. So let me talk about this one instead. Can somebody tell me if the work here is enough to tell that the answer to this part of the question?
Yeah, it's enough to answer that because there's still going to be a pivot in every column and every row going through. So that means that we're going to have a unique solution.
Yeah, so it didn't matter what the vector here was. It didn't matter because like if I put any other vector here, it's going to row reduce, and at the end there's going to be some other vector here, but because the row reduction of the matrix itself is going to be exactly the same, so yes for -1, 2, 0, and yes for any b. It is yes for any b because I have a pivot in every row, okay, of the matrix A. So that tells me that in fact this spans all of R3. Okay, so the span here is in fact all of R3. So it's yes, it's just for so it is just here and it is just here. Andrew is asking for an explanation of -1 to 0. Would you say yes, because there is a pivot in every row and there is a unique solution, or do we not have to explain ourselves? The explanation here would be that I get my matrix, I row reduce it to this matrix, and once there is a pivot in every row, that means that there is going to be a solution for any b. So you do have to explain that yes, it is in the span of this because when I row reduce the matrix A, I get a pivot in every row in the row reduction of A. That is enough to say because that actually implies that the span is all of R3. So in fact, every vector is in the span. If it was not, if you get to this point and you do not have a pivot, for example, in the third row, there will be some vectors that are solutions and some vectors that are not solutions. But in this case, because the span is all of R3, every single vector will be in the span. Okay. So now, the part B, by the way, of 4, it just rephrases that is -1 to 0, a linear combination of, is exactly the same question. Being in the span is being a linear combination of those vectors. So it's exactly the same question. It's just it can be asked in two different ways. Is it in the span of the two vectors, or is it a linear combination of those vectors? By the definition of span, those are the same question. So let me see what's in number 5. Before I go to number 5, are there any other questions about this number 4? Okay, so let me copy and paste number 5 here. First with this part. Copy, come back here, paste it, not so large. All right. So this is another question about the span. So is 1 to 3 in the span of the columns of A? Let's start by reducing the matrix A. But I just in case it doesn't work out that these columns span all of our three, let's row reduce with 1 to 3 already in mind. So I have to solve 1, 1, 0, 4, 5, 3, minus 1, 0, 3, and I'm going to row reduce already with 1, 2, 3 in there. 1, 4, minus 1, 1. I'm going to reduce the second column, the second row. So this minus this, 5 minus 4 is just 1. 0 minus minus 1 is 1. 2 minus 1 is 1. And then I have 0, 3, 3, 3. So I was right to keep in mind 1, 2, 3, because in this exercise, the solution is going to be different from the previous one, because when I keep row reducing, the last row is all zeros. So that means right now, it means two things. It means that because there is a row without a pivot, it means that these columns do not span all of R3. But for this matrix, there is no pivot in the augmented column, so it is consistent. Okay, so this is good news. Here it is that it is consistent. There is no pivot here, so let me write that here. No pivot here means that columns do not span R3, but that is okay in this case because this system is consistent for this one vector. This column here with no pivot is a free variable. And that tells me that there are, so the no pivot here, this good news here, plus this, tell me there are infinitely many solutions. And therefore I can now just keep going. Do they ask me, is the question, is 1, 2, 3 in the span of the columns of A? So actually I don't have to answer the question more than yes. System is consistent. If one of you wants me to find the solution, I will keep going and find it. I find one solution, but the question doesn't ask me that. And for the sake of time in the exam, you should just answer the questions that are asked and not go and give more detail than you need to. Okay, so this system is consistent. So for this one, the answer is yes. So for this question here, yes. What about this one? 3 to 1. I have to reduce again, but now with a different augmented column. 1, 4, minus 1, 1, 5, 0, 0, 3, 3, and row reduce with 3 to 1. So this is 1, 4, minus 1, 3, row reduce, 0, 1, 1, 2 minus 3 is minus 1, and then 0, 3, 3, what did it, oh, and 1. Let's row reduce the last row, 1, 4, minus 1, 3, 0, 1, 1, minus 1, 0, 0, 0. I'm subtracting 1 minus minus 3 is 4. And now you see that that is a problem. I'm going to put it in red right here. This is a pivot in the augmented column, means inconsistent. So this is an example of a vector that is not in the span. So this is, for this one, the answer is no, and that is not in the span. So it means that in the, if these are V1, V2, and V3, then what we've just shown is that 3, 2, 1 is not in the span of the columns of A, which are V1, V2, and V3. Okay, but the first vector was in the span. Any questions on this? Let's see what the other, did I just do here? To width, no. To height. Do we need to state that 3, 2, 1 isn't in the span of V1, V2, V3? Yes, because it says the question itself says, what about 3, 2, 1? And is asking, is it in the span of the columns of A? So what about 3, 2, 1? I guess is no, it just says no to that. But just to be more clear, I'm saying that no, the vector is not in the span of the columns. Okay.
I guess this is a good time to ask, but how verbose do you expect us to be on the exam? Like, do you want us to write out like every single step and equation and altered matrix we create?
The more verbose you are in exams, the better. Because if you mess up, not for my exam, any exam, if you mess up along the way, I can see where you're going. So if you just give me, if you have, I don't know, I don't know that I'll have like scratches of paper. You write some scratch of paper somewhere, I can't see what you're doing, and you just tell me what the row reduction is without any steps in between, then I don't know how you got it. If you just like invented a row reduction of the matrix or like what you did, so I can't give you partial credit. If you show me first of all the row reduction steps, then I can see, okay, you made a small arithmetic error in here, you got to here, this is wrong, but you are drawing the correct conclusions, then I can try to give you some partial credit for that. So the more verbose you are also in like, why do I know, like everything I said in here in the first part of the problem that I said, I know this is consistent because there is no pivot in the augmented column. If you just marked this, can you see my laser when I use the laser? If you just mark, excuse me?
Yeah, we can see
Okay.
it.
So if you just wrote this, reach this augmented matrix, and you write here, and then just mark this and say consistent, and then say, yes, the system is consistent, I'm going to assume that you know what you're talking about. But just to be super verbose, and actually I think it would be better, is when you say things like this, no pivot, just also talk about more about the pivots and say here, no pivot in the augmented column means consistent, means yes, system is consistent, and yes, there is a solution. So yes, this is in the span of the columns of A. The more words, the more keywords you use, as if I was a ChatGPT agent or something that I'm trying to understand what you're doing. The more keywords you use, then the more chances I have of giving you partial credit if you messed up. If I know you are arguing in terms of pivots, even if it's wrong, at least I see that, okay, you got to the wrong place, but you know how to argue in terms of pivots, and then you are saying like, yes, there is a pivot here, so it's inconsistent. Um, at least you did part of the work is correct. Does that make sense?
Yeah, that makes sense. And then the idea between like problems 4 and 5 is the idea that if the matrix can be reduced to like a consistent row reduced echelon form that any like that it'll span all of R3 and anything will be included. Whereas if there's like a free variable or if it's inconsistent, then you'd have to then that may not be the case.
Yeah, and we haven't talked about dimension yet, but what's happened, the difference is that, let me go back to the previous slide, is that this matrix has 3 pivots. That means that these columns span all of R3, so it doesn't matter what vector you put in here as AX equals B, what vector you put here, every vector will be a linear combination of these 3 column vectors, and then it didn't matter what vector I put in here as the right column vector I get here. I have these 3 pivots in a 3x3 matrix. I'm good. This matrix is going to, these vectors are going to span all of R3. The difference is with these one that we do not have 3 pivots when I row reduce the matrix. What that means is that these 3 column vectors are linearly dependent. So what that means is that the span of all 3 vectors is actually equal to the span of 2 of the vectors. So I could come up with a linear combination of the 3 and say the span of all those 3 vectors, the span of 2 vectors. So these 3, what they are actually spanning, instead of all of R3, they're spanning a plane in R3. So there's a lot of vectors that are missing from the span. And then some vectors will be in the span, like 1, 1, 0 is in the span, and some other vectors, like 3, minus 1, 4, is not in the span. Because of the number of pivots in here, it's telling me that I don't have all of R3, so some vectors will be in the span and some vectors are not in the span. And you can tell whether the span is all of R3 or not by the number of pivots in the row reduced matrix of the columns. Oh yeah, Andrew, you don't have to write it in set notation. You can just write it in words if that's what you mean. Yes, absolutely. No, 3, 2, 1 isn't in the span because the system is inconsistent is a perfectly fine answer. Yeah, that's good. All right, what else? Other questions, other types of questions?
Could we do 6A and 6B?
6A and 6B. Okay, let me again. Where am I going now? Here, next slide, paste. Not so huge. All right. Suppose S is given by these 2 4-dimensional vectors. Give an example of a vector in the span of S, but not in S. So first of all, what is the span of S? The span of S will be, this is vector, let's say U, this is the vector V, then the span is all the possible linear combinations, every lambda U plus mu V for lambda and mu in the real numbers. Okay, so every possible combination, linear combination. So something that is in the span but is not in S is, for example, if I do U plus V, that is in the span. In here, lambda and mu are both 1, and that is not U or V. So U plus V in this case is the vector. I just add the coordinates 1, 2, 0, 3 plus 0, 1, 1, 0, and that is the vector 1, 3, 1, 3. So this is in the span. but this is not in the set S itself, right? The set S itself only contains two vectors. The span is infinite. So this is just one vector that is there, but it is not in S. And then part B, let me just copy it down here. Part B says, give me something that is not in the span. And that's a little bit trickier, but not too tricky, because again, what is the span? If, say, W is in the span, then W by definition, okay, by definition of span, has to be a linear combination of those two vectors. So it has to be a lambda u plus a mu times v. And I can write a formula for those. This is lambda times, I know what u is, 1, 2, 0, 3, plus mu times 0, 1, 1, 0. And that will be, I can just scale and add, that is lambda, 2 lambda plus mu, 0 times lambda, and so this is then mu, and then 3 lambda. Okay. So now, how do I find out a vector that is not one of these vectors? Well, for example, you can see that lambda and 3 lambda, or that this coordinate here has to be 3 times this coordinate, right? So the first one, this last one has to be 3 times the first one. So any vector that doesn't satisfy that, so if I just put 1, 0, 0, 5, that cannot be in the span. If this one was of this form, then that would mean the first column of the first entry would tell me that lambda is 1, but the second entry would tell, the fourth entry would tell me that 3 lambda is equal to 5. And that is impossible. So that tells me that the vector 1, 0, 0, 5 is not in the span of S. Okay. By the way, if somehow you didn't see this, you can also like try your luck, because the span of S is 2-dimensional in a 4-dimensional space in R4. So it is sort of like tiny. It's like a 0% of R4. So if I pick a vector at random, it's probably not going to be in the span of S. I would have to be very unlucky to get a vector that is actually in the span. The question is, does not in S mean not equal to a column in S? No, it's, wait, hold on. So if you are asking about this part, in part A, it says not in S. S itself has two vectors, one vector and two vectors. S only has two vectors, u and v. So not being in S means, yes, the vector is not one of these two column vectors. There's only two elements in S. It's not this one and it's not that one. Not being in the span, though, the span is infinite because it's all the linear combinations of these two. So it's every vector of this form. So there's infinitely many of them. So I have to find one that is not in the span, and that is an infinite set. Yeah, there's only two vectors in S itself. Is there's a set with only two vectors, but the span itself is infinite. Okay. I think it was Ben. Is this clear? Did you ask for number 6 yourself?
Yeah, I did. I'm just wondering on the bottom left equation, 1005 equals
Yeah.
delta and stuff. I see how we got 1 and 5, but if lambda equals 1 and
Yeah.
mu equals 0, would that mean that like 2 times 1 plus 0 in the second row would not be 0? Like, does that matter?
Well, I'm just saying that this is actually impossible. So I'm
Okay, so it doesn't matter.
it doesn't matter. I mean, it makes things better for us because we're trying to show that this vector is not of this form, right? So what I'm saying is the way I argued is that if this vector was of this form, then the first row tells me that lambda is 1, the fourth row tells me that 3 lambda is 5, so lambda cannot be 1 and 5/3 at the same time. It's impossible. I'm done. But what you're saying is that, okay, so if lambda is 1, then this is 2 plus mu, so mu has to be -2. Okay, I can match that, but then mu is also 0, so mu would have to be -2 and 0. So you can argue several ways that this is impossible. I just argued
Okay.
in one way, and by the way, I picked this 1005 sort of at random. I picked it because I knew from these equations it tells me that the fourth one has to be 3 times the first one. So that's why I picked 1005, but you could have picked many other vectors that are not in the span.
Thank you.
Yep. Other questions, other problems to work on. Whoa. While you think about it, give me a second. I have to. Let's see. 9, 11, 12. Let's go to 9. Write 2, 2, 4 as a linear combination. That's another linear combination. Let's see if 11 is different. Why don't we do 11 or 12? And then maybe go back to 9. So, so this is the transformation we want to show. It is linear. So first, let's show that the map is linear. So that is a transformation. We can show that it is a linear transformation in 2 different ways. First of all, let's show that T of u plus v is T of u plus T of v. So here T of x, y, z is x plus z, y plus z. So let's take u is going to be u1, u2, u3. V is going to be v1, v2, v3. And then T of u plus v is T of, if I add those 2 vectors together, I get u1 plus v1, u2 plus v2, u3 plus v3. Then if you apply the transformation says add the first and last coordinates, so u1 plus v1 plus u3 plus v3, and add the second and the third. So U2 plus V2 plus U3 plus V3. Now, what do I want to get at is eventually I want to get to T of U, T of V. So let me write that down. T of U would have been U1 plus U3, U2 plus U3, and T of V is V1 plus V3, V2 plus V3. And now I can see how I can break this vector here into a sum of two vectors, because I can, this is 3. So I can put the u's together. This is, let me, instead of writing it like that, I'm going to write it as U1 plus U3 plus V1 plus V3 and U2 plus U3 plus V2 plus V3, which is equal to, now I can break it as the sum of two vectors, which is T of U plus T of V. So it satisfies that first property of linearity. The second property of linearity is that, let me write again, that T of X, Y, Z is X plus Z, Y plus Z. And now I need to show that T of lambda U is lambda T of U. So what is T of lambda U? That is T of lambda times U1, U2, U3. That is T of lambda U1, lambda U2, lambda U3. By the way, I'm writing fast, but I am going to send you the PDF of what I'm writing, and I will also post this link, the video of this as a link. Now T of this is lambda U1 plus lambda U3, lambda U2 plus lambda U3, which is the same as lambda U1 plus U3, lambda U2 plus U3. And now I can take a common factor of lambda. This is scale. This is the scale of scaling this vector. And this is, well, this is just lambda times T of U. Okay. So it does satisfy the second property of linearity, and therefore, yes, it is linear. Okay. The second option is that actually we know that matrix transformations are linear. So if I write T of X, Y, Z, which is X plus Z, Y plus Z, and I am able to write it as a linear, as a matrix transformation, we have seen in the theory that matrix transformations are linear. But this is the matrix 1, 0, 1, 0, 1, 1 multiplied by X, Y, Z. So this is a matrix transformation, and matrix transformations are linear. And then I'm done. Okay. But once again, here you have to say that. You have to say, if you're going to use this, then you have to tell me that I can write it as a matrix transformation, and that matrix transformations are linear by theory. Therefore, this transformation is linear. Okay. By the way, part B, it says determine the standard matrix for T. Which is, I have done it myself. So how do we do that? We do that because if I have a transformation, then the standard matrix will be T of the canonical vectors as columns. Okay. This transformation that we have in our hands it goes from R3 to R2. So it will be a matrix with 3 columns and 2 rows. Then if I compute first what is T of the first canonical vector, so of 1, 0, 0, that is first plus third, which is 1, and second plus third coordinates is 1, 0, so I get 1, 0 there. T of 0, 1, 0 will be 0, 1, and T of 0, 0, 1 will be 1, 1. So that's why there is the second column is 0, 1, and the third column is 1, 1. So this is the standard matrix. Okay, and I can, this one is this column, this one is this column, and this one is that column. Okay. The third part of this problem is T onto, oh, there's 2 more parts. Is T onto, is T 1 to 1? So let me now write T of X, Y, Z is 1, 0, 0, 1, 1, 1 of X, Y, Z. And we want to ask is this 1 to 1? And is it onto? How do we tell if they are 1 to 1 or onto? It's all a matter of pivots. So I have to row reduce. So I start with my matrix and row reduce, but this is actually already in row reduce echelon form. So I am done. So in principle, I would have to row reduce, but I'm actually already done. And this is in row reduce echelon form. And then I look at pivots. I have a pivot, I have a pivot, I have no pivot here. Okay, so what does that tell me? It tells me that, first of all, there's a pivot in every row. That means that the columns span the columns are in R2, so they span all of R2, which is the codomain. They span all of R2, and that tells me that T is onto. Okay. However, there is not a pivot in every no pivot in every column. What does that tell me? It tells me that this is not 1 to 1, or that the system AX is 0 has, in fact, infinitely many solutions. And that tells me that T is not 1 to 1. Okay, so pivot in every row and pivots in every column tell you whether it's onto or 1 to 1. So by row reducing, I can tell what is happening. Before I go to number 12, which is the same but just a different map, any questions about this problem? Yeah, so what I said is that to to say that a matrix, that a transformation is linear, you either have to prove the properties of linear, this and this, or another way of doing it is to show that it is a matrix transformation, which it is, it's exactly this matrix transformation, and then say that matrix transformations are linear. So yes, you have to say that T is a matrix transformation, give me the expression as a matrix transformation, and mention that you're using the fact that matrix transformations are linear, which is something that we know from the theory. Yes, yes, that's what. So this was alternatively versus this is sort of like method one. Method number one was to show this property and this property, and you need to know how to do both because I mean the problem could ask, you know, they could ask you directly prove that T of u plus v is equal to T of u plus T of v. Okay. Let me go to number 12. In number 12, the transformation is in this case from R2 to R2. It's clearly a linear transformation also because it's x1, x2 goes to 2x1 plus x2, x1 minus x2. I can compute the matrix for this will be, again, what is T of E1? The first canonical vector goes to 2, 1, versus the second canonical vector that goes to 1 minus 1 times x1, x2. So it is a linear transformation because it's a matrix transformation. This is the matrix for it. And now I can do also answer if it is one-to-one and onto by row reducing. This one is not in row reduced form, so I row reduce to this one instead. And then 0, 1, minus 2 is 3. So this row reduces to 1, minus 1, 0, 1, which row reduces to the identity. Okay. So there is a pivot in every row and in every column, but in particular, a pivot in every row tells me that is onto, and a pivot in every column tells me that is one-to-one. So it is both one-to-one and onto. All right. Once again, when you're solving the problem, I would like to see the row reduction, as many steps as you can. I want to see the row reduction at the end. Would like to see that you are indicating how many pivots are there, what are the pivots, so you can tell me that yes, there's a pivot in every row because of this, and it's onto, and there's a pivot in every column. So it's like this. By the way, once I've reached this form, this is already an echelon form, and I can see that there are pivots in every row and every column. So I could have stopped in this step and already conclude these two things. Okay. Let me go to, somebody had asked also about number 9. So in number 9, I actually have to write, so for number 9, I have to write 224 as a linear combination of 1, 1, 0, 0, 1, 1, and 1, 0, 1. We do that as if I write those 3 columns as the columns of a matrix, what I need is to find x, y, and z that will give me 2, 2, 4. So what I need to do is row reduce this matrix. So I have to start from 1, 0, 1, 1, 1, 0, 0, 1, 1, 2, 2, 4, and row reduce from here. Okay. This will be 1, 0, 1, 2, 0, 1, minus 1, 2 minus 2 is 0, and then 0, 1, 1, 4. This row reduces to 1, 0, 1, 2, 0, 1, minus 1, 0, 0, 0, 1, minus 1 is 2, and 4. So this is 1, 0, 1, 2, 0, 1, minus 1, 0, 0, 0, 1, 2. And this is 1, 0, 0, 0, 0, 1. Just going to add them up. You get 0 and 2, 0, 0, 1, and 2. Okay, so what that means is that x is 0, y is 2, and z is equal to 2. And I can try it out. So 0 times 1, 1, 0 plus 2 times 0, 1, 1 plus 2 times 1, 0, 1. That is going to be 0, 2, 2 plus 2, 0, 2, which is 2, 2, 4, like we wanted. So that works. So this linear combination is equal to the vector we wanted. In part 9b, this was part A, they asked me if those three vectors are linearly independent. So in part B, let me just write it here because I want to copy from this row reduction. So are these linearly independent? And the answer is yes, because I want to, if I want to know if they're linearly independent or find a dependency, I have to row reduce the matrix with these three vectors. And if you look at the matrix here, forget about the augmented column, as I row reduced to the identity matrix. So since the column with these vectors row reduces to the identity matrix, the vectors themselves have to be linearly independent. So the columns, if this is v1, v2, v3, and you make the matrix with v1, v2, v3, and row reduces to the identity, that means that they are linearly independent. And the third question asks, do these vectors span R3? So they will span R3 if when I row reduce, there is a pivot in every row, which again, there is. When I row reduce, there's a pivot in every row. So therefore they will span all of R3. Okay. All right, everyone. I actually, so it's 1:37. I need to bring one of my kids to the doctor. But let's see, Andrew, for part B, could I also say that there are pivots in every column? For part B, that they're linearly independent. Yes, you can also say the linear independence is also equivalent to there being pivots in every column. So yes. Yep. Okay, so everyone, let me know if you have more questions by email or just reach out, and good luck in the exam. Okay, I'm going to stop
Thank
the
you.
recording.